Hello, everyone. Welcome to Pre-Lecture 5. This is going to be for our pre-lecture for class on the September 14th. So just a reminder that this is not going to cover any of the material that will be on quiz number 2 that will also be that day in class. Okay, so this material will be for quiz 3 the following week. Okay. So we're starting chapter 11 with this pre-lecture, and in chapter 11 we're going to talk a lot about solutions. And so you should remember, hopefully from general chemistry 1, what a solution is. It is a homogeneous mixture of 2 or more substances. And we're going to define that a bit more specifically, and then go through different types. And so solutions are made up of 2 major components, one of which is the solvent, and that is going to be the majority component. So whatever the majority amount that we have is, that's going to be called a solvent, and then whatever our minority component is, that's going to be called a solute. Okay. When a solid dissolves in water, molecules of the solute become uniformly distributed amongst the molecules. And that is an example of a solution forming. Okay, so an example of that, this is just the chemical formula for sugar that you could find at your table. Sucrose is the chemical name for it. And if we were to put that sugar into water, it would dissolve and form a solution. Okay. So in a way, this is a phase change, and we tend to designate it in Gen Chem. We're working in water, and so it goes from being a solid to being something dissolved, and so we designate that with the AQ in our chemical equation, meaning something that is aqueous. Okay, water is often our solvent, but a solvent can really be, again, anything that is the the majority component in any sort of homogeneous mixture. Okay. And so some examples from your textbook. So we can have solid solutions, actually. So if you mix 2 metals together, you can form an alloy. An example of that would be 5-cent coins in the US. So nickels contain both the element nickel and the element copper. Air, what you're breathing right now, is also a solution. It contains nitrogen as the solvent because that is the majority component. We also have oxygen and several other gases, and then we can have, a whole mix of things here in order to form different types of solutions. Okay. These are the characteristics we could use to describe them. I'm not going to read them out for you. These come from your textbook. If you would like to take notes on them, you can, of course, pause the video or look back at the slides at any point and find them here. But if these are helpful, great. If not, these kind of particular definitions of what characterizes a solution, we're not going to cover beyond this slide. So when we form a solution, typically we start with 2 different things. In this example, we have 2 gases. And so in order for a solution to form, it must be a spontaneous process. And later on in the semester, we'll define what spontaneity means in terms of energy and chemical systems. But for now, essentially, you can think of it as something that will not require energy input from any sort of outside sources. Oops, sorry. And so in this example, we have a bulb with helium, a bulb with argon, and when we turn the key in order to essentially create a passage between those 2 bulbs, a solution will form between the 2 gases because we essentially have a spontaneous mixing process. Okay. This can be a bit more complicated if we think about something like a solvent and a solute that are maybe both liquids, or one is a liquid, one is a solid. If we're thinking about how the solution would actually form in terms of our intermolecular forces from chapter 10, we have to break all of the bonds, intermolecular bonds that are holding together our solute, and break them out so that there can be mixing, and same with our solvent. Again, we have to break those intermolecular bonds. And the key here is that when they mix, when they form this homogeneous mixture, they must come together in a way that releases more energy through the interactions, the new interactions, new intermolecular interactions between the solvent molecule and the solute molecules. Okay, so that's how we end up with step 3. Okay. Right, a key measure of something from solutions is going to be a solute's solubility. And so the solubility of something is a particular to each solvent, and it is defined as the maximum concentration that can be achieved under the given conditions when the process is at equilibrium. And so that will become a key factor for some of our other definitions here. And so, for example, if we were dissolving salt in water, we'll reach a certain point where the solution would become saturated. And what that means is that is the point at which the solute's concentration is equal to its solubility. So we would call that a saturated solution. At every point before we reach the point of saturation, we would call our solution unsaturated. We can also have something called supersaturation, and this is where we actually have more solute than should be normally allowed in our solvent, but we have not reached an equilibrium state, and so it is not considered to be saturated, but instead supersaturated. So an example of this would be if you have soda pop, for example. When you open it, some carbon dioxide is released, but we still have carbon dioxide that is dissolved in our mostly water. Of course, we could call it soda pop as the solution of a number of things, but until our solution kind of goes flat, we would say that our soda pop is supersaturated with the amount of carbon dioxide. Okay. Right, we also have things called electrolytes. And so for substances that dissolve in water and form ions, those are called electrolytes. And substances that when they dissolve in water do not form ions are called non-electrolytes. And so we can break them up into different categories too, where we have strong electrolytes or weak electrolytes. That is just dependent on how much they ionize when they're dissolved. So for example, we have acetic acid here that only partially dissociates in water when it's dissolved. So we'd call that a weak electrolyte, whereas something like potassium chloride, KCl, fully dissociates in water. We'd call that a strong electrolyte. And if we have ethanol, that does not dissociate, meaning it is a non-electrolyte, okay? And so I would highly recommend checking out this link I put in. If any of you have ever seen the movie Idiocracy, it's a clip from that movie. Essentially, they have a sports drink that is similar to Gatorade in this movie called Brondo that they use to water their plants because it's got electrolytes, and electrolytes are what plants crave. So I'd highly recommend watching that clip. If we think about how electrolytes interact with the solution, so again, if our electrolyte is KCl, that's going to be our solute. As it dissolves, we're going to have new intermolecular forces, intermolecular bonds that form as it dissolves. And so this is it starting as a solid, as KCl. As it dissolves, we then basically have a hydrogen bond interaction with our ion, which would make this an ion dipole intermolecular force interaction, right? And so the partial positive of the hydrogen would interact with the negative of the chloride, and then the partial negative of the oxygen would interact with the positive of the potassium, okay? This is going to be a favorable energetic interaction. That's what causes things to dissolve. Again, we have to have a favorable intermolecular interaction in order for things to dissolve. If we think about pure water, that's going to be a poor conductor because it is a covalent molecule, meaning, again, it doesn't readily ionize when it is just a solution of pure water, okay? Same with things, other non-electrolytes like nitrogen gas or sugar, right? Okay, that's it for today. If you have any questions, please feel free to email or feel free to send me a message or ask in class. Good luck studying for quiz number 2, and I will see you soon.